It's my pleasure to be here, and today I want to talk about a different subject in earth sciences, the Anatolian block movement motion. If we can simulate this through 3D DIC. What I want to talk about is to the detail first. Where are we? What is earth sciences? What are we trying to do? Talk about some tectonics. What is Anatolia? What is tectonic physical modeling in the world and in our country? What is our laboratory? What kind of experiments we do? And I will show you two movies in the end time. So this is where we are. If you look interior to our planet, we have an upper crust, lower crust. The thickness is between 5 and 60 kilometers here. The upper crust is brittle, and the lower crust is kind of ductile. Then we have an upper mantle, mesosphere, lower mantle. This is maybe 2,000 kilometers. We have a D layer here, a liquid outer core, which works as a nuclear generator actually. And we have a solid inner core. Nowadays we have another matter here. It's a very new publication. So what is earth science or geoscience? It's an all-embracing term referring to the fields of science dealing with the planet. There are many branches of earth science, or we can call geology, which I'm a geologist, I'm not a geophysicist. Structural geology deals with deformations, structures, and the motions of the crust mainly. Plate tectonics is a subdivision of tectonics or structural geology. It's a scientific theory that describes the large-scale motion of Earth's lithosphere. Lithosphere includes the upper crust and the lower crust, some parts of land. There is a theory which in the 1940s about continental drift. It says, and seafloor spreading, which it says the upper crust is brittle and it's made of plates, and these plates are moving. This is the world map, and these are the plates. These are the continents that we know, but this is the actual plate boundaries. And there are many movements as shown in the arrows. Like this, the Atlantic Ocean. The Atlantic Ocean spreads like this and cuts island with a knife just in the middle. As you know, we have a volcano here, Barbaduba, nowadays. What else we have? We have the South American plate here, and we have the Nazca plate here. The Nazca plates subducts under South America like this. And when it subducts, this is the Pacific Ocean. This is the Pacific Ocean. When it subducts, it goes melt underneath the South American plate, and magma goes up, and now, as you know, we have 10,000 or maybe 15,000 kilometers long mountains here, and it's all volcanoes. Here we will go in detail, but we have smaller plates, like the Arabian plate. These plates move very slow, like our nail growth rate, 3 centimeters in a year, something like this. The plate boundaries are here, as shown in the first map, and 95% of the earthquakes and the volcano activities happen on these plate boundaries. This is the ring of fire, maybe you know this. Most of the earthquakes happen here, but also we have some strange things going on here, like the Africa is now separating at the moment. This Somali peninsula is going counterclockwise and separating from Africa. So in maybe some million years we will have another sea or an ocean here like the Red Sea. That's why we are having a lot of active volcanoes in Ethiopia and things. And these are the volcanoes, active volcanoes at the moment. Again, you can see the ring of fire coming from Alaska, Kamchatka, Japan, Philippines, and things. So, when we look in detail, the upper crust and the lithosphere, or the lower crust and asthenosphere, there are some movements, 3 types of upper crust movements we can see. Some are divergent, some are convergent, some making some shear. The ocean crust, which has a density about 3 grams per square centimeter, subducts until under the continent and then melts here and goes as volcanoes here. And these plate movements create some structures which we call faults. Faults are the breaking of the upper crust, the brittle upper crust. Before faulting, it is something like this. And if there is a tension, if you pull the crust, we call it normal fault. This is the fault plane. This is the hanging wall. This is the footwall. Because of the gravity, the hanging wall just drops. We have several big faults like this in the world. If you compress the crust, we have reverse fault, like the one in Indonesia in 2004, the big tsunami. That was a big thrust, which the length of the fault was something like 1,000 kilometers, and the slip was 20 meters. It was enormous. And if there's a shear, we have 2 types of, we call it strike slip faults. This we show here, left lateral strike slip fault, and the other one is right lateral, like the San Andreas fault in California, or the North Anatolian fault in Turkey. And we have some other types. Now we're coming close. This is our subject area, which nowadays the contours may change. If we come close, there are many movements. These upper crust movements create a lot of faults. This is North Anatolian fault, which is a right lateral strike slip fault, which means this part goes right, this part goes left, 25 millimeters per year. This, the length is about 1,500 kilometers. And in the last 100 years, maybe 1,000 people died in this area because of the earthquakes. This is the second biggest fault. This is a left lateral strike slip fault, which means this part goes left, this part goes right. And here's the African plate. The African plate subducts, which means this, under Anatolia and the whole Europe continent. Subducts, and the end of the slab turns and pulls back what is above. So if it pulls back, when it pulls back, it makes some tension, like you see here. These are normal faults. So this part, the Aegean part of the western Anatolia, is opening like this, like my fingers, and we have many normal faults here, which we call grabens. We have normal faults here, we have right lateral strike slip faults here, left lateral strike slip faults here, and we have reverse fault here because Arabian plate collides Anatolia and goes underneath. Anatolia is going upwards. So there are many movements. These are the earthquakes in the last century. In 100 years, red ones are magnitude, moment magnitude above 8. Blues are above 7. Yellow ones are above 6 magnitude, and green ones are above 5 magnitude. This is a summary of the motion in this area. So Arabian plates collides Anatolia with a speed of 18 millimeters per year. Anatolia goes above Arab plate. Anatolia goes like this. This is Anatolia. Okay? And Eurasia is, you can think this as a wall. It is not moving. We can say that. Africa plate here, as I said, subducts during these lines, these orbs, subducts under Anatolia and under Europe. So it is like a cherry. You hold a cherry and squeeze it, and the seed just goes out. So this is the seed of the cherry, simply, with a speed of 25 millimeters per year. But towards southwest, southern Greece, the speed goes more because African plates pulls this part. See, these are all normal faults. This is North Anatolian fault, this is East Anatolian fault, and this is the Dead Sea fault, which is very, very important fault too. These are the tectonic plates from Rehlinger. These are the GPS velocities from Rehlinger again, Rehlinger 2006. Relative to Eurasia, we say this part is fixed. And Arabia is moving towards north, counterclockwise. This is Iran moving north and collides this part and Iran, which we call the Zagros Sutur. And this is fixed. Arabian plate subducts under Anatolia and Europe and pulls back Anatolia, so the velocities increase here. This is another summary. These are the velocities. See, Somalia is separating now. That's why we have so many long lakes in Africa, like Niassa, Tanganyika, Albert. These are 500-kilometer long lakes, maybe 20 kilometer width. That's why we have long lakes. These lakes will be a sea in the future. So Arabia is counterclockwise movement to north. Iran has a similar thing. This we can call fixed. This is moving westwards and then southwest. This is subsection of the African plate. So what is why am I showing this? We are trying to simulate the upper crust. You know, it's very complicated and heterogeneous and anisotropic. So models are representations of natural structures. They are used when direct analysis of various aspects of natural structures is either difficult or impossible. Two types of models, one physical, the other is mathematical, as you know. There are three types of models, again, rock mechanics, photoelastic and geometric. Okay, I pass the long things. In 1812, Hall made the first physical modeling experiments with clothes. He made some compressions, some shears and things, and he published this in 1815. This is the first wheel. These are some very important physical modeling and mathematical modeling references, if somebody is interested. This is an example from the upper brittle crust. This is a fold. This is an anticline, an asymmetric anticline. When the material is not so brittle, it's like ductile. You can, and if you compress it, you can make it fold. If it's getting brittle, it fractures, and fracture means fold. This is a fold. This is another fold. Anticlines, synclines, they always, we can see on, these are this is a normal fold. This is Andes Mountains in South America. This is the hanging block. This is the foot block. See how many meters, maybe hundreds of meters, the blocks have slipped. This is another fault. This is a fault. This is another fault. This is another fault. This is a normal fault. See, this layer is here and here. So because of tension, this block, which is the hanging block, falls down. This is the strike slip fault from 1999 Turkey earthquake, which 35,000 people died. This is a right lateral strike slip fault. Goes from here. This is where I live. So coming to the experiments slowly, this is the sandbox. This is our first machine, in our first small laboratory. Then we have slightly tried to improve it. This is a sandbox machine which we designed and made it. It can go up to 2 millimeters per hour speed. There are two walls. This is wall one. This is another wall. They can come together or go apart, or we can make some shear. First, before PIC, we were just trying everything by manually, but it was impossible. You know, we used some MATLAB and things. This is another. This is not ours actually. You can see some normal faults here. This is the cross section. So last year, with the help of Peter Meckel, we have finally established our dream. This is our last laboratory. There are 34 laboratories in the world, and this is the only one in our country. So this is our sandbox machine. This is what we have, cameras and things, the workstation. We use different materials: clay, detergent, soap, cream, cheese, yogurt, flour, sand, honey, to simulate the brittle and the ductile materials. Here we make some Play-Doh by ourselves, and above that we used some flour and speckled with the black spray paint. And we are trying to make a shear. And these are the starting of the legal cracks. As you know, the resolution is enormous in big 2D and 3D. We are very amazed of this. And after an experiment, we can see this. But as you know, there are no black spray paints here, or no speckles, whatever. So these will be losing in our analysis. We don't do speed photography. We can make 4 or 5 in 1 second. So final very simple test. Last week we have done. We just wanted to see if we can do something about this map. This is the Arab plate. This is Eurasia fixed, a heavy stone. This is the Africa. Africa will pull, this will push, and this will be fixed. And we will make, we want to make Anatolia here with the Play-Doh, which is a ductile lower crust. So as everybody knows, we try to calibrate with small papers and things, the field of view. Then we put the flour on Anatolia, 1000 RPM, which is about 10 centimeters per hour. I should say this too. These movements in the upper crust happen in millions of years, like in 10 millions of years they move like this. And the dimensions are enormous, 500 kilometers. But in the laboratory, of course, we have to do some scaling. We have to make it fast. So 10 million years, we make it in half an hour. So 500 kilometers, we make 50 centimeters. Also, the material properties should be scaled too, which is not very easy. So this is the final thing. We sprayed, but it's not a very good spray as you see. Those toggle things, calibrations, adjustments of the cameras, calibration plates. Also, the counterclockwise motion of the Arab plate, because it's not colliding like this. It's going counterclockwise collision. So I put my hand into the ruler and I was turning the ruler when at the same time this wall was pushing. So these are the first cracks. This is the North Anatolian fault. We have tried slightly, we have managed. This is the East Anatolian fault. This is the final map. See, there are normal faults happened here. This is the Asian part, Western Anatolia. This is Africa. Africa is pulling. Because it's pulling, it's making tension. We have normal faults and grabens here. And because of the cherry seed, this part moves left. And we have a strike slip fault here, right lateral strike slip fault. And we have a collision boundary here. We have mountains, which we have actually. And this is one of the final photographs. This is the displacement vectors. This is a right lateral strike slip fault. See the vectors. This is going right. This is going left. So thank you, and I want to just show you maybe two movies. Okay, this is during without any analysis. Okay, this is Anatolia. This is Arab plate. This is the Eurasia, Caucasia, and Russia fixed. And here is Africa pulling. So you can see the collision here. Mountains start. It's going up. And see the strike slip fault started. Okay, there are some things which we didn't want to have. We were expecting faults like this actually, but this is only the first experiment for Anatolia. of course, we have a lot of noise because of those black spray point. This is Arab, this is Anatolia, Russia, and Africa pulling. These are the Z values in millimeters. It is about 2 millimeters here now. See the collision here. Because we are losing the black points of spray, see, we have lost this. We have Z values going down here because of the normal faults, the Grabens. This is all I want to say. If there's any questions? Yes?
Just one comment. Maybe it was due to my bad training. You just need to set starting points to continue evaluation left and right of the crack.
No, we have done the polygon. You mean that?
No. When there's a crack, you just force the system with different starting points, so it continuous correlation, like left of the crack and right of the crack. So you said it stops because of this crack, the correlation.
Yes.
But you can continue when you set
starting points.
Starting points.
So you don't lose the data.
Maybe it was my
But
fault.
that's not just because of the spray point, because there is no spray here. I mean, in the crack, there is no black point.
No, but when it continues, it stops correlating. It just keeps on going on the right upper end.
Yes, here.
And if you set several starting points around, then it doesn't matter if you have a crack in the middle, then you correlate
right.
left and right.
I forgot that.
You forgot it.
Yeah. Okay.
Just how do you establish your material properties? You're looking at like a huge mass of heterogeneous material. Is it trial and error, or is it?
Well, as you know, nothing. It's very difficult, and we will never make the perfect thing. We are just learning, and it's really. If you change only one parameter, as you know, everything changes. If you add some flour in honey, everything changes. If you change the thickness, everything changes. So it's really very difficult. We just try. Yes.
I assume you guys went back to history, right, and verified your model. Is this future or past?
This is what we are doing at the moment.
Right, but did you go back and verify what you guys?
No, we didn't have
You
time
had to do that, right? Otherwise, it's really complicated.
This application in earth sciences is not very common in the world. Well, okay, in mechanics and other things, aeronautics, it's common, but in earth sciences I have maybe seen one or two in the world.
Where people went back to history and then predicted the present, and then you kind of. Otherwise, I don't know.
No, we will make it anyway.
When I look at Caltech, I think they use satellite images and digital image correlation to actually do tracking from satellites.
Yes, but that's the INSAR. That's not digital image correlation, but they are using satellites for. That's another technology.
They've done digital image correlation, aren't they? They're trying to do it, for sure.
But where are you going to put the cameras?
Satellites.
They're using INSAR. You know INSAR.
It's from science.
First, we thought maybe we can use INSAR in the laboratory.